And in the last class we did introduced what is known as canonical ensemble. Okay, and where we have used the postulates of equal a priori to derive what is known as Boltzmann distribution. So I hope you remember, you are following. I'll just show you one slide. So yeah, yes. So can you see?
Yes, sir, we can.
So we had started like this. So we have ns number of systems, and each system has n number of particles or molecules. Okay, and we then constitute a super system where you have ns times n number of particles. Total volume is ns times v. V is the volume of each system, and then you have total energy, which is given by this. And you have these two constraints, isn't it? Sum over of nj is equal to ns, sum over of nj ej equal to e total. So I can think of a system which has n number of particles or molecules. Vt is the volume and et is the energy. And then we can construct a micromechanical ensemble starting here with this description, isn't it? And there we introduce or use equal a priori postulate. So I said that if I have distinguishable objects, rather objects, I would say, you have ns number of systems, and then systems are distinguishable, and you can cluster them into n1, n2, n3, and many ways you can do. So this is the number of ways you can do this, given by this expression. And I told you that that the collection of nj within the second bracket, curly bracket, is actually the distribution. So if I ask a question, what is the probability of observing a given state nj with energy ej, it has to be equal to this, given by this. It is not nj by ns, it is rather nj average over all the possible distribution of nj divided by total number of systems. And this is given by this expression. So this omega gives you the number of ways. Essentially, it can be arranged. So this is the distribution which you use to calculate the average of nj. So this is nj average, shown here. And I said that, okay, this nj average will have contribution from different arrangements, but then there will be one arrangement which is the most probable and which will have the highest contribution. Okay, each of them are equally probable. Okay, all the possible all omegas are equally probable, but what I'm saying that, okay, there will be one arrangement which will be most probable, and then I replace this sum with this most probable arrangement. So my pj becomes nj star divided by ns, where ns is the total number of systems. I suggest please read the book by Mercury. I hope you have started reading the book by Mercury for this part. Have you?
Yes, sir.
Yeah. So then I take a log of this, and then I take a derivative of this with respect to nj with the constraint using Lagrange's undetermined multipliers alpha and beta to take care of the constraint shown here. And if I do the math, and I see, I showed that we showed that the pj is given by this, where the denominator is called canonical partition function, sum over j exponential of minus beta ej. Then we showed that, okay, it is possible to show that beta is equal to 1 over kVt. We did it extensively in the last class, isn't it? And also we calculated some thermodynamic quantities such as internal energy, average pressure, all in terms of, and Helmholtz free energy, all in terms of this partition function, canonical partition function. And I think also the entropy, eventually also we did entropy. Okay, and then we said, okay, we will do something else today. And today another ensemble we're going to discuss, this is called grand canonical ensemble. Okay, So today's discussion is also from the book by Professor Bakchi, Biman Bakchi, and Macquarie. It's a combination of these two books. So please go and read after today's class. Okay. Okay. So let us see what is there today. So the grand canonical ensemble is as follows. Okay. Here the number of particles can fluctuate, can vary. So it is not, n is not constant. Okay. What is constant? Temperature and V. How you make temperature constant? You know that you have to couple this with a temperature bath, as we did in case of canonical ensemble. But n is fluctuating, but there is something which is constant. This is called chemical potential. You have a one component system, and this is done by coupling this whole system with a particle bath, which has infinite number of particles or molecules. Okay, so there are two baths. One is temperature bath, another is particle bath. Okay, and then you follow the same procedure. The one we followed for canonical ensemble, we follow the same procedure here. So let me write down. Okay, so we follow the same procedure here. So let us write down. Now you see that, let me write down few things. Say n, you had nj in case of canonical ensemble. Here I have a different notation. I have n, small n, capital N, j, and this is number of systems in the ensemble that contain n molecules or n particles, what you want to call it, doesn't matter. That are in state J. Okay, so n and J, okay, is nothing but the number of systems in the ensemble that has n number of molecules, capital N number of molecules. Okay, and these n number of molecules are in the state J, energy state J. Okay, is this clear? The statement, it is not very difficult.
Yes, sir.
So basically, I'll have to calculate this set of this distribution. Actually, this I want to actually is a distribution. Actually, this is I want to calculate. So as we progress, it will be clear. Now, all these arrangements are equally probable within that angular bracket, okay? Because this is equal a priori postulate. But it has to maintain some condition. Can you tell me what are the conditions in case of microcanonical? Can you guess? If you can guess, it will be nice.
So could you explain your question once?
My question is, this distribution is in all the possible arrangements are equally probable, okay? But they are subjected to some constraint, the conditions. In case of canonical ensemble, what are the constraints? You remember the conditions?
N, B, and T.
Yes, similarly, you'll have constraints here also. Can you tell me what are those constraints?
This is mu Vt.
Yeah, mu Vt is okay, but what are the constraints in terms of N and J? See, the first constraint is, the condition is, of course, if I sum over all possible values of N and J of this number N and J, what will be the answer? Can anyone tell me?
NS.
It has to be NS. But you see, you have a extra sum over N because N can fluctuate. You understand? So NS is the total number of systems in the ensemble. Huh?
Yes, sir.
Okay. Now we have another constraint. What is that constraint? Again, if I take a sum over n and j with this n and j times e and j, what will be the answer?
E total.
Total.
Yes, this will be total energy of the ensemble. Okay. And then this is very important, that if I take another, this is another constraint which you did not have here there, but if I do this n nj times n, this will be what? Look at it very carefully. You don't know what is this, but this will be some number, isn't it? This will be the total number of particles or molecules in the ensemble. You understand? Ensemble has, you understand, no? Each system, what is n? N, you remember? What is capital N? Tell me.
A certain number of molecules or particles in the state J.
Yes, yes. So basically, if you multiply this to and sum over all possible j and n, this will give me something like another number, which will be some nothing but total number of molecules in the ensemble or particles. Okay, so this is another condition. So number of states for a particular distribution is, you know, this omega. Can anyone tell me what is this? You know this answer. This is, you know, ns factorial, but here it will be slightly different, isn't it? You'll have product over n as well, isn't it?
Yes, sir.
This is fine. Okay.
Yes, sir.
And the distribution that maximizes, actually we take log and maximize that. Okay. This omega subjected to appropriate constraint, you know the constraint which is written. Completely dominates all others. This is exactly what we did in case of canonical ensemble. You remember, no?
Yes, sir.
So what will be the next step? Tell me.
Constraint extremization.
Yeah, so I take a log. Now, can anyone tell me why do I take log and then extremize?
Easier algebra, maybe.
One is this, and there is an inherent thing. You actually know that all these omegas, they are huge number in number, no? Huge, exponentially large. If I have n number of particles, it is exponential of n. So if I take log of that, it becomes something like it grows with the number of particles, isn't it? And then we
Yes.
extremize that. Yes, then we extremize that, because you see that log is something which is very useful throughout. You will see that log of this will give you some thermodynamic function, because this extensive variable like entropy, it has to be extensive, means it has to be proportional to a number of particles, isn't it? It's a function of n. It should have, if you make the number of particles twice, then entropy should also become twice, isn't it?
Yes, sir.
Yeah, so you will see that log of all the omegas, whatever you call, this is very useful in this case. Anyway, we'll see. Not exactly log of omega, but you'll see that it is actually, you'll get some kind of partition function and take log of that partition function. Partition function is also kind of accessible phase, isn't it, volume. So we do this. I want to do this in detail because it is not done in any course. It is very useful that you do it once. And also you get used to. So what will be the ln ns factorial minus ln this is fine. If I do anything wrong, tell me. I can do some mistake. I am doing it. I hope it is not boring for you, but it is very important that I do this, because otherwise you'll never learn in your life. I'm telling you, in chemistry. N ln n minus n. This is starting approximation. Now you see log of product of some factorial. You know, this is sum. That you understand, no?
Yes, sir.
This is sum of over n, sum over j. If I do anything wrong, you tell me. Is this convincing? If I write like this, Anish. Kailash is there today, or he is not there today as well?
Yes, sir. Seems okay.
Okay. So this one is this. Okay. And if I expand this, what I'm going to get? Inside the sum, I'm going to get convinced? What is this last term?
NS.
So this
And it should
last,
be a plus.
yeah, plus.
It should be plus.
Yeah, this is what? This is ns, and this will cancel, isn't it?
Yes, sir.
And what you will be left with? You'll be left with this. So I have ln omega minus sum over n, sum over j. Okay, this fine?
Yes, sir.
So basically now I'm going to maximize this. So what I'm going to do, I'm going to do d del nj of, I hope you remember, ns ln ns minus this is fine. But then you have constraint. What are the constraints? You have like this, alpha nj nj minus beta nj okay. But then you also have something, one more. I put gamma. It's fine.
Yes, sir.
That has to be equal to 0. Now if I differentiate the first term, what I'm going to get? 0.
0.
Yes, sir.
What I'll get from the next term? I'll get two terms. No, I'll get something like n_nj by n_nj, okay, minus ln n
And NJ.
nj, isn't it? Minus alpha minus beta e nj minus gamma what n. This is fine. Is this fine? I hope I have not done anything, any mistake. Anyone has a problem? Tell me. I hope this is fine.
Just one thing, sir. The derivative should be with respect to n and j, right?
Yeah. So notation is slightly, you have to change this notation. Yes, you're right. N j. This is fine, na? Okay.
Yes, sir.
So the first term is -1. So basically, what I can do, I just rearrange this. If I rearrange this, what I'm going to get? This is nj star actually. If you put ln nj star, I can write it like it is -1 plus alpha minus beta nj. Okay, and then I'm calling it minus alpha prime minus beta nj minus gamma n. Okay, is it fine? So if I
Yes.
take exponential on both sides, I get this is equal to fine. I hope this is not a problem.
Yes, sir.
And okay, and I know that what I want to calculate is something like p nj, which is a function of v, beta, and gamma. This is equal to n j star divided by ns. This is what you want to calculate, no?
Yes, sir.
So let us see what happens if I calculate that, what I get. Okay, so I know what is the value of ns. Ns is sum over n, sum over j, n nj. If it is for n nj, it is also true for this one, isn't it? Okay,
Yes, sir.
this is what I want to do. Now I go back. What is n nj? N nj is given by this one. So I have to take a sum of this. So what I have here is so our n nj is e to the power of minus alpha prime e to the power of minus beta e nj, and this is going to be a function of volume, and e to the power of minus gamma n. Okay, this is fine. If I do any mistake, tell me. And this is equal to e to the power minus alpha prime. I can take it out. Okay, and what I have here is this. This is your ns. Okay, this is your ns. Then what is p of nj? Which is a function of v, beta, and gamma. This is, as I told you, has to be equal to this one divided by this. So this one, you know, e to the power of minus alpha prime divided by ns. Ns is So this one will cancel alpha prime this one. So what I have here, I have this is equal to e to the power of minus beta enj minus gamma n divided by this sum, whatever the sum is. I use a notation like this. Okay, this is something like this notation. Okay, and this is a function of v, beta, and gamma. So this thing I'm calling it what are there in denominator? This part. This one I'm calling it this. Okay, this is fine. This is a neat expression now,
Yes, sir.
and we will see that later. We will see this is called. You can guess. This is there's a name. This is called
Grand canonical partition function.
yeah. This is called grand canonical partition function. This is done in 408. I'm sure. Was it done in 408? Or at least somebody should tell, na? Every day I ask and nobody answers. Don't remember anything from 408? Anish? Anish, you
I
took
have
it,
not
no?
done it yet. No, sir. I'm in second year.
Okay, who has done it? Let me see who has done it. Nobody has done 408 here. Deepak is not there today. Anyway, so this is, we'll see, this is called grand canonical partition function. We'll see it later. Okay. So let us again calculate. Let us calculate this. Let's calculate, say, average energy, E bar or whatever you want to call it. If you, I was using E bar or I was using angular, I think, no?
E bar.
E bar I used in the last class. What
Yes,
notation I use?
E bar.
E bar, which is equal to, I can use any notation. Okay. Now this is equal to, and you can, of course, this E bar is a function of V, beta, and gamma, and this is going to be equal to something. We'll see. But before I do that, so let us take this guy and take a log of this. Okay. If I take log of this, what is this? Log of okay, this is fine. Now if I take a derivative of this with respect to this log of this, say with respect to beta, what I'm going to get, tell me. Okay, of course I keep other thing constant like V and gamma constant. We did that, no? In canonical,
Yes, sir.
the argument will come down. The argument for the log, and then in the numerator, what I'm going to have? I'm going to have my sum is there, but I will have minus Ej, isn't it? Into e to the power of minus beta. Now I go back to E average definition. It is 1 over the partition function, sum over n, sum over j, Ej, sorry, Enj, not Ej, it is Enj, e to the power of minus beta Enj, so the function of volume, minus gamma n. This is a definition, no? So what is this? This whole quantity? This whole quantity is nothing but minus of, are you convinced? Tell me.
Yes, sir.
Anyone has a problem? Onish is only saying that. But others should also say. I hope they're listening.
Yes,
What is
sir.
Yes,
what is
sir.
this? This is your whatever this function, isn't it? A minus sign will be there. So actually now I have expressed, for example, if you want expressed internal energy, whatever the notation you want to use, is equal to minus of d ln. So you are convinced? So now I can also use this partition function to express internal energy, to find internal energy. I can find internal energy. Okay. Any question so far? Now can anyone tell me how do you calculate, say, average pressure? What should you do? It's not very difficult, because if I take a derivative of this with respect to what? Volume. What I'm going to get? Tell me what I'm going to get. I'm going to get the argument. Anyone has a problem? Tell me. Because the argument of log, and then what will happen inside the log? Tell me. Tell me what is going to happen. See, function of volume is E. So
Sum
basically, what,
over
yeah,
nj
sum over
del e
n,
del
sum
e
over
del v
j, but minus
del e del v del e
del
nj del
nj,
v.
del nj, del v into e to the power
Keep-
minus beta enj e to the power minus gamma n. Okay. And this is actually, if you go back, you see that it is actually average pressure. If you compare, you go back to your previous day's note, huh? In your canonical ensemble, that is actually equal to average pressure. You remember this? This is actually equal to average pressure,
Yes, sir.
because it is actually, it is nothing but, it is something like your average of kind of thing, isn't it? The whole thing. This is average pressure. You go and check, because I am not going there in detail, but you should be able to see that. Of course, when you take the derivative, you have to take the derivative by keeping beta and gamma constant. Okay. So I have pressure, average pressure. What about average number of particles? N bar, or whatever you want to call it. This is also going to be equal to thermodynamic pressure, no?
Is it del e del gamma average?
Yes, has to be, no? Because n bar means I have to bring this n out, down, no? I have to differentiate respect to gamma.
Gamma.
Yeah, okay. So actually one can do that. You'll see that if I take this partition function, log of that, and differentiate respect to gamma, keeping this beta and v constant, you will get 1 over this thing will come down, which is this one. Sorry, I should careful while writing. I'm not writing it again and again, so I'm just writing the final expression. This one, then I'll have a minus sign, minus 1 times n j n this is what you have, no? You're going to have this.
Yes, sir.
Yeah, please say yes, sir. At least, I don't know, someone should tell, not always Anish. What is this guy? Tell me.
Average n.
This is minus of n, isn't it? So in other words, n average is Be very nice, isn't it? Very nice. See, I know if I know the partition function, then I can actually generate so many things. Use this. It is nice, isn't it?
Yes, sir.
Yes.
Hello, sir.
Yes.
Sir, in the average pressure, won't there be a beta also? Minus beta.
Yes, there will be minus beta. Minus beta. Why? Because you are calculating. No, we are to. Why it is minus beta
So while taking the derivative
with respect to
with
v?
v,
Yeah, you are calculating with respect to v. Yes, I think so. Anish, did I do anything wrong here? Any mistake? Beta. What was that expression? Okay, this is the expression. I take a derivative with respect to v. So exponential of this, exponential of some function of v, and then this, yeah. Then a function. Then you take a derivative of that function with respect to, of course, there will be a beta,
Yes, sir.
isn't it? There will be a beta. Somewhere I have to put it here. Okay, so I think with that the notation is like that, I think. Okay, so with that, this is the definition of P. Okay, there's a typo. So, but this is how you calculate your average pressure, average energy, and average number of particles. Now, what is beta? I'm not going to do it again. I have done it for canonical ensemble. You know that you can follow the similar procedure and you can show. Beta is 1 over kBt. Okay, but rather I will try to do something else, which is like here. So let us define a function. Say, let us say that if it is this function log of this quantity, which is your I'm calling it partition function. I'm calling it a function which is a function of beta, gamma, as well as is a function of enj. This is fine if I write like this. I hope this is fine, no? If I write like this. Any
Yes, sir.
problem? Yeah, which is nothing but your log of sum over n. Actually, the expressions are so big. Every time you write, there is a possibility that you have a typo. This is fine. This is how it is. Now I know this is a function of beta, gamma, and this enj, set enj. Now if I take a differential of this, what is there on the right hand side? It is del f, del beta, keeping gamma constant and all other enj's constant, into d beta. This is fine if I write like this. I hope you can follow.
Yes.
Now del f, the next time is del f by del gamma, beta constant, and then I can also have, see, this is del f by del enj, but you have to remember that there are many ways you can have nj's, enj's, so you have to have a
Understand.
sum, isn't it?
Yes, sir.
Enj, and then here you have beta, gamma, and all the other enj's. No, you understand what I'm saying? This is how it is. Okay, is this fine what I've written?
Yes, sir.
Now what is the first term? Del f, del beta. Del f means del ln by del beta. You remember what is this? This is nothing but minus e of, isn't it? Go back to your previous slide.
Yes, sir.
I'm not, well, this is how it is defined. No, f is ln of that, this special e. So this partition function. What about the second term? This is del f. If you
N
go
bar
back and see, this is minus n bar. You'll see.
minus N bar.
And what about the next term? Can anyone tell me what is the next term? So in order to understand the next term, you do it here. Take ln of this. Sorry. How many of you are taking 560? How many are taking? Tell me. I don't want to see tell me in words. How many are taking? Some people are taking, no?
I think
560.
Vatsal is the only one.
Yes,
Hmm?
sir. Yes,
Some
sir.
people,
Some are.
some are taking, no?
Yes.
So okay. Because I want to do Fermi-Dirac and Bose-Einstein later, so for that I just want that information. Anyway, this is N J. This is a definition, no? Now you take a derivative of this with respect to what you are going to get. Tell me. You are going to get
Minus beta, I have 1 by kVt.
yes, and then minus beta will come. What else? A particular NJ you are calculating, no? What you are going to get here? What you are going to get? Tell me. You are going to get are you convinced? Hey, Anish and others.
Yes, sir. Yes.
Ramanand. So basically, and one term. So this is what this carefully you'll see that what is this part. Now this part is without the beta. What is this? What is this? Tell me. This is
The
minus
distribution.
minus beta times something like PNJ, isn't it? Huh?
Yes, sir.
So what? So then what is the third term then? A third term is going to be minus
Yes,
beta
yes,
times sum over n sum over j p nj times d e nj. Fine? Is this fine?
Yes, sir.
So this is actually like ensemble average reversible work done, isn't it? So ensemble average reversible work done by the system. Okay? Any problem, you just tell me. We'll stop.
Why is it called ensemble average of reversible work?
Because if you go back to your previous day's note, you will see this is how it is done. Because it is so if you go back to your previous day's note, I have to go back and see. If you go back to canonical ensemble note, you remember that we had a term which is like p dv kind of thing in that expression, p times dv.
Yes, sir.
So you go back and check. Go back and check. You will see. You go back and check that you will see that this is how it is. So we issue okay this part, okay, only this part. So only if I have only assuming PV work, sometimes if I have only PV work, then I can write that df equals to minus E bar d beta minus n bar d gamma plus beta to PdV. This minus PdV term, you just go and check your previous day's note. Okay, if you have problem, we can talk. Anish,
Okay, sir.
previous day's note,
Okay,
you
sir.
had that one term I defined, because you remember that this is uh, uh, that term was said it is equal to PdV, actually the pressure times. So if I now, this is with the negative sign, so this is how it is. Okay, this equation is fine. Okay, only if I assume PV work. Now add, then adding to both sides. This equation, if I add both sides, what I'm going to get? What I have here is d of
df
f plus
beta E bar.
gamma n bar. What you get on the left hand side? So let me write down whatever is there. What will be the two terms? So first term is d of beta E bar. So it will have beta d bar plus E bar d beta plus gamma dn bar plus n bar d gamma. This is fine?
Yes, sir.
You can simplify this. If I simplify this, what is going to happen? This guy will go. Anyone? This guy will go. We'll have three guys left, isn't it? So what I have here is d of whatever, I don't know, f plus beta E bar plus gamma n bar is equal to beta T bar dv plus beta T bar. I hope you are convinced. This is fine. I don't see any
Yes.
problem with this. Okay. Now, this is the equation, no? So now let me write down another equation which you know from thermodynamics. If I write down, you'll understand this. You know, this is this from thermodynamics, I hope. Okay, that TdS equal to dE plus PdV minus mu dN. You know this from thermodynamics.
Yes, sir.
Okay. Now also beta is 1 over kB T. Okay, beta is 1 over kBt. If beta is 1 over kBt, this term, so this will become now 1 over kBt. So actually what I can do, I can multiply both sides by kBt, then you'll have kBt what you will have on the right hand side, because beta is 1 over kBt, no? I just multiplied both sides by kBt. This will become 1, no?
Yes, sir.
What about this?
Gamma KBT.
And also I can, this one I can write it as T d of kbf plus, now beta is 1 over kbt. You multiply this with kb. What is going to happen?
1 over
E
t.
bar by T.
Plus kb gamma n. This is equal to okay. Now you compare this equation and this equation. The equation number say 1 and equation number say 2. If you compare this two, what I'm going to get? You compare 1 and 2, what are you going to get? Tell me.
S
You're
is
going to
equal to
you have to integrate, but I'm just integrating with putting the integration constant 0. What I can get here, first of all, right hand side, if I compare, you will see that what I get, that minus mu is
KBT
kbt times
gamma
gamma, which basically means your gamma is minus mu by.
minus mu by KBT.
This fine? This is one thing you get. And also when you integrate, you have to integrate, and you get something like S, which is your entropy. This is equal to what? Your kbf plus E bar divided by temperature plus kb n bar. Of course, gamma you can replace with minus mu by kbt. So this will give you kbf, you know. Minus n bar mu by t. And this is actually the expression for entropy. So let me write down one more time. S is but this expression for entropy in grand canonical expression ensemble. Okay, so now you got expression for entropy in grand canonical ensemble. We had expression for entropy in canonical ensemble in the last class, isn't it?
Yes, sir.
You had it.
yes sir.
Remember, no, you had it.
AB log q plus e bar by t.
Yes. So now if I go back and write down the final expression for this quantity, which is a function of v, beta is like t, gamma is like mu. This isn't it? And this is going to be equal to n j e to the power of minus e n j v by kVt e to the power of mu n by kVt. And this is called, this is a full expression for grand ensemble remember we had this canonical partition function. What are the expression? This was okay.
Yes sir.
And you had also, we got the expression for entropy in terms of this. What is the expression? Expression is I think it is like that, isn't it? Let me check.
Yes, sir.
N bar mu. Yes. Anybody remembers the partition, the entropy in terms of canonical partition function?
E
KB
bar
log
by
Q.
T plus KB log Q.
It was E bar by T plus
KB log Q.
kV.
ln Q.
So actually you can express entropy in terms of canonical partition function or canonical partition function depending on in which ensemble you are working, isn't it? As simple as that. So now I give you two problems which is given in the assignment set. You calculate entropy, for example, for same system, same problem, but in two different ensemble. First you do it in canonical, then you do it grand canonical. Calculate entropy or calculate any other quantity. You will see they are identical. What does it mean? This
So
is
that is
called,
expected because it's a state function.
yes, and this is called equivalence of ensemble. So essentially all the ensembles are equivalent. Depending on your experimental setup, you go for a particular ensemble, isn't it? But you calculate thermodynamic quantities, you can calculate using any ensemble, they will be same. We call equivalence of ensemble. Very loosely I'm talking. Okay, is this clear? And if I want to write it further, I can write it like this. The sum is actually, I can always say the sum is n0 to infinity because infinite number of particles can be there. So if I do this, you can say is this clear? Can I write like this? Just look at it. Look at this too. Basically, actually, you can express your grand canonical partition function in terms of canonical partition function. And also you can further simplify this saying, okay, I define a quantity lambda and your lambda is say exponential of mu by kBt. It's a lambda. Then this is going to be nVt e to the power of, sorry, not e to the power of
Lambda to the
Lambda
power
power.
of n.
n, yes. It is this okay? Is this okay?
Yes, sir.
Now what is the thermodynamic function for this ensemble? Thermodynamic function means if I take log of this partition function, I'll get some thermodynamic function. No, what is that?
E minus Ts minus mu n. Is that it?
Um, kind of, but yes, you're right. Almost there. You're right. How do
I
you
mean,
do
if
that? How do you know that?
I just rearrange the entropy equation and multiply it by K minus kBt.
Yes. So basically, you
Minus-
just do it from coming from there, and actually, if you rearrange this, you will see that okay, I just multiply this Ts becomes E bar plus kVt ln epsilon minus mu n bar. Okay, this is how it is. Or in other words, kVt ln this guy is equal to Ts kVt ln this guy equals to Ts plus mu n bar minus E bar. And can anyone tell me what is this quantity? This Ts what is this quantity? Anyone know? So I'll give you a hint. Your Gibbs free energy is this mu n in one component I'm doing now. And this is equal to Gibbs energy definition. You know what is that definition?
E plus PV minus TS.
Okay, so it basically tells you that mu n plus Ts minus E is equal to PV. So this is actually nothing but, isn't it? Or in other words, in canonical ensemble, what was that? What was the harmonic function?
E minus TS, which is Helmholtz free energy.
Helmholtz free
It was
energy.
Helmholtz free energy. It was minus remember, no?
Yes, sir.
So my next question is, I should go to which ensemble so that my natural thermodynamic function is Gibbs free energy? I should go to which ensemble?
NPT.
Where,
NPT.
yes, yes. So I should go to isothermal isobaric ensemble. This is clear. The next thing would be, I am not going to do it in detail, but if I go to isothermal isobaric ensemble, it is NPT. Okay, then I should have a partition function in that ensemble as well. And if I take log of that partition function, I should be able to relate this to some thermodynamic function. And what is that thermodynamic function? As you rightly said, somebody, Ramanand, what is that partition function? Ramanand, what is that partition function? Thermodynamic function?
Can you repeat, sir?
What is the thermodynamic function in this ensemble?
It gives free energy.
Yes, it will be Gibbs free energy, isn't it? Is this clear? I am not going to do it because I don't think there will be repetition if I want to do it. So actually, I'll just write down this equation. Okay, that in isothermal ensemble, if I calculate, this is the partition function delta. Of course, you know that this is going to be sum over E and sum over V. Here, pressure is constant, so the walls are flexible. The volume can change, and this is going to be equal to, actually you can call C show. This is NV, this mechanical partition function times okay, this is called isothermal partition function. And if I take a log of this will gives you minus kVt of log of this will give you Gibbs free energy. This will give you Gibbs energy.
That is delta of NTP, no?
Yes.
The logarithm.
Yes. Sorry, I put it like this. Yes. This happens when you have so many things to write. Okay, so this is the expression. Now what I have written here, can you understand this one? Why I put omega there? Because this is obvious, because if I go back and look at, for example, the canonical partition function itself. So can I express canonical partition function in terms of grand canonical partition function? That is the question. I should be able to know. Sorry, microcanonical partition function. I should be able to, isn't it?
So which in terms of which?
Microcanonical partition function. Can I do this? So check this. How you get this? Just check this and we'll see. Now we'll calculate something else now. I go back to again canonical ensemble. Huh? So I go back to canonical ensemble and I know that my definition of E bar or EJ, sorry, not EJ, E average this way. You remember this? This is 1 over I'm writing beta. Okay, this is fine. Is this fine
Yes,
if I
sir.
write this way? I hope this is fine because this is not a very difficult thing to do. This is your definition of E bar. Now I can calculate also this one, E square average. What will be the definition? It will be is this fine?
Yes, sir.
Okay. Now I can always define mean square standard deviation for a system. This is done in one of the classes, no? What a definition? What was the definition? Mean square standard deviation.
Square root of expectation value of squared quantity minus
It
the
is actually, I remember that E minus E average, take a square of that and then take an average, isn't it? And this is, if you expand this, we have done, this is nothing but E square
E
average
square average minus
minus E
E
average
average square.
square. E square average minus E average square. Okay? It's not very difficult. And what is the definition of heat capacity?
Del E,
At
del T,
constant
and
volume. And this is NVT, no? This has to be equal to
Del U del T at constant volume.
is the definition, no? Now I want to see whether you can heat capacity, I can relate this to mean square standard deviation. So let us see. Let's see what its capacity is. Okay. So before we do that, let us go back to my definition of E square average. Any notation you can use. Okay. This is equal to 1 over Q. I don't want to write NVT again and again. I'm writing 1 over Q. This is fine. This is fine, no?
Yes.
Like this. Now this one you can always write it as, see, I am just doing a trick. 1 by Q del beta of J Ej. Okay. Can I write like this? I can. Because if I take the del beta of this Ej will come down with minus sign. This minus will become plus. Isn't it? It will become Ej square sum over J. Isn't it? And 1 Q is there. So this will go
Yes,
back
sir.
to this. This is just a small trick I did. Is this clear? What I did?
Yes, sir.
If it is not clear, tell me. Now what is this quantity? This quantity is nothing but your E average times Q.
Q.
Isn't it? So the whole thing I can write it as 1 over minus 1 over Q del beta of E average to Q. Can I write like this?
Yes, sir.
Now the next thing would be 1 over Q. So if I take derivative of that, of course, what I'm going to get? I'm going to get the first term is going to be Q. This is fine.
Yes, sir.
So this first term is going to be,
Minus del E by del beta.
yeah, just updating, yes. So the first term is going to be minus, and this one is what? This one it is, can I write like this? Tell me whether you can write like this.
Yes, sir.
Yes, sir.
And what is this? This is, you remember what
Proportional
is
to N.
this? This is
Proportional to N.
minus E average. This one, remember,
Yes, sir.
because your E average was, if I go back,
Minus d ln Q by d beta.
of course you have to keep N and V constant, which I'm not writing again and again. Okay, so this will give you this, fine. On your left side you have, so what I have here is E square minus E whole square. This is E whole square, no? This is E average,
Yes,
okay,
sir.
which I'm calling it, of course, sigma E square. This is equal to minus del E del beta. Now what is beta?
1 over kbt.
Now what is the answer? What is this there? Then this is sigma E square is equal to del beta is what? Del beta is what? This will
Minus
be,
kbt square.
and the minus is there, no?
And so, but minus plus. Del E del T.
Of course, now I'm writing N and V constant. So in other words, it is,
CV.
Sorry. So basically, your mean square deviation in energy, sorry, mean square standard deviation in energy is a measure of your heat capacity at constant volume. Okay? You have done the math at least. Okay? Basically, this is very important. And this heat capacity, basically I'm getting it from the mean square standard deviation of energy, isn't it? So if I go to another ensemble and if I have another quantity and I calculate mean square standard deviation of that quantity, I can also relate this to some kind of phononic quantity. We'll see what is that. So in the next class, we'll start dealing with this. This is called fluctuations and response function. See, this heat capacity is a kind of response function. So, and sigma E square is a measure of fluctuation. So the equilibrium fluctuation, this is fluctuation in equilibrium, is related to some kind of response function. So heat capacity means I supply some amount of heat, and what is heat capacity? You know that heat capacity of substance means what is the amount of heat required to increase the substance temperature by 1 degree. 1 kilogram of substance by 1 degree, isn't it? This is the working definition of heat capacity. So actually you have an external agent here. You're adding heat. Okay, you're adding heat and you're then looking at the response of your system, but your system is in equilibrium. So this is, in this case, it is the heat capacity at constant volume, which is measured, which is obtained from the mean square fluctuation or deviation of your internal energy. Similarly, if you can measure the mean square fluctuation or deviation of your enthalpy, you will get something else. Can you guess what is that?
CP.
Yeah, this will be CP, and you have to work in NPT ensemble. If you work in NPT ensemble, you will see that sigma H square, H is enthalpy, is equal to CP times kVt square. So similarly, you can have volume fluctuation or number fluctuation. That will also give you another response function. Any idea what would be that response function?
Number fluctuation should just be chemical potential or related to it, right? For a one component system at least.
Actually, this is called isothermal compressibility. If you go to volume or number fluctuation, isn't it? We'll see that in the next class. But the whole thing is that if your system is in equilibrium, then the root mean square fluctuation is a measure of that of the energy, internal energy gives you heat capacity. Okay, and number fluctuation will give you isothermal compressibility. But one more thing which we will do in the next class, I don't want to do it today. I can briefly tell you, because I can always calculate, for example, I can always calculate this quantity, that okay, what is sigma E divided by E. Okay, and can you tell me how does it scale with number of particles? Yes, sigma E scales as what and E scales at what? So the question is, how does it scale with, or how does it, yeah, depend on
n power minus half.
yes,
The
has to be.
back of the envelope calculation.
Yes. And you will see it is 1 over root over n. So higher, so if you have a bigger and bigger system, this fluctuation, this relative fluctuation, this is called relative fluctuation. This relative fluctuation will be narrower, will be smaller and smaller, smaller and smaller, isn't it? Because if I go back to your Gaussian distribution, you remember that this will give you E average, no? Isn't it?
Yes, sir.
And this will give you minus sigma E plus sigma E. This is your kind of, isn't it? So if I go to a system with more number of particles, your distributions will be narrower. So basically what you have here is you have, this is your average quantity, and in a system within equilibrium, that quantity fluctuates around this average, isn't it? And this measure of this fluctuation is given by your sigma E, if it is energy. And the larger the system is, smaller the amplitude is. The relative fluctuation is less, isn't it? Because average also increases, and the relative fluctuations also. So the ratio is root over n, 1 over root over n. Now can anyone, can Anish tell me how it is 1 over root over n?
I just did a very rough estimate. So if sigma
Yeah,
is
you did perfectly well. Perfectly.
if sigma e square goes as CV, then sigma e goes as root CV, because you can take T to be intensive.
Yes.
So if it goes as root CV, then it must also go as root n, and E goes as n, so root n by n.
This is like this, no? Because this will go the root n, isn't it? This is root over of CV. It has to be root n, and then E is n. So this is, and this is actually signature of equilibrium fluctuation. And this is fantastic, isn't it? Now, if I have a fluctuation in the total dipole moment of a system, and that fluctuation has to be related to something of that substance. What is that? Response function, any idea? You're getting my question, I hope. And that response function is called dielectric constant of a medium. This is related to the fluctuation in your dipole moment, total dipole moment of the system. Okay. Similarly, if a magnetic system, if you look at the fluctuation in magnetization, this will be related to what is known as magnetic susceptibility. So this is another response function, magnetic susceptibility. Okay.
Yes, sir.
So we'll stop here. We'll do this little bit in the next class. Eventually start Fermi-Dirac Bose-Einstein. But before I do that, what I need to do, I think I'll do a little bit of molecular system. Just briefly, I'll tell just vibration and rotation. And you got the assignments, no? Please solve the assignment, send it by 12 midnight. Okay? You're solving
Yes,
that,
sir.
because this will also give you an idea about the quiz, about the mid-sem. Okay? The mid-sem is, I think, after 24th, isn't it? 24th and 28th, between this. Something like that, isn't it?
Yes, sir.
Mid-sem? I guess so. So please, you're following the course, I hope. But I don't see more than 18, 20 people participating, but I don't know. And I just hear 3, 4 voices. Others are there or they're sleeping, I have no idea. Hey, Batsal, are you there?
Yes, sir.
Yeah. Siddharth? He is not there, but he is online. Shubhangshu?
Yes, sir.
Sana?
Yes, sir.
Okay, but you should speak up, no? Sometimes if I ask a question, if I make a mistake, you should tell. You're following the course?
Yes, sir.
Yes, sir.
Okay, good. So with that, I think we'll stop today. And the next class is on Thursday. Okay? Okay, thank you very much. I'll now stop recording and